Module 4, Systems Thinking, Part 2. Developed by Jan Smuts in the 1920s, contemporary systems thinking is a de facto cross-disciplinary approach to bringing discipline to the chaos of overlapping systems. Sometimes taking a bird's eye view helps you to see patterns and connections that wouldn't be obvious, discernible, or even discoverable on the ground. Wikipedia, that brave experiment in collective intelligence, says, quote, "For some, systems thinking is the cognitive process of studying and understanding systems of every kind. For others, the focus is integrating information from different sources and different types. A system may be defined in general as a set of interrelated or interacting elements. This definition accommodates both passive structures, for example, a necklace or the Dewey Decimal System, and active structures. However, most systems theorists focus on activity systems in which structures or components interact in behaviors and processes." End quote. Biology is the obvious candidate for productive systems thinking because of the sheer complexity of the behaviors and processes involved in sustaining life. But the more our machines grow in complexity, the more systems thinking has been embraced by engineers, particularly as artificial intelligence expands. Formal systems theory as we know it was expanding in 1940 by the biologist Bertalanffy, and became part. Formal systems theory as we know it was expanded in 1940 by the biologist Bertalanffy and became part of the new science of cybernetics thanks to Ross Ashby in the 1950s. In his 1956 classic An Introduction to Cybernetics, which defined the field with its section Cybernetics and Requisite Variety, important because it embraced diversity, Ashby wrote, quote, "It has been found repeatedly in science that the discovery that two branches are related leads to each branch helping in the development of the other. The result is often a markedly accelerated growth of both. The infinitesimal calculus and astronomy, the virus and the protein molecule, the chromosomes and heredity are examples that come to mind. Neither, of course, can give proofs about the laws of the other, but each can give suggestions." Ashby wrote, quote, "It has been found repeatedly in science that the discovery that two branches are related leads to each branch helping in the development of the other. The result is often a markedly accelerated growth of both. For example, the infinitesimal calculus and astronomy, the virus and the protein molecule, the chromosomes and heredity. These are examples that come to mind. Neither, of course, can give proofs about the laws of the other, but each can give suggestions that may be of the greatest assistance and fruitfulness. Here I need only mention the fact that cybernetics is likely to reveal a great number of interesting and suggestive parallelisms between machine and brain and society, and it could provide the common language by which discoveries in one branch can be readily made use of in the others." Ashby talked about the complexities of the system. He wrote, "The second peculiar virtue of cybernetics is that it offers a method for the scientific treatment of the system in which complexity is outstanding and too important to be ignored. Such systems are, as we well know, only too common in the biological world. In the simpler systems, the methods of cybernetics sometimes show no obvious advantage over those that have been long known. It is chiefly when the systems become complex that the new methods reveal their power. Science," he said, "stands today on something of a divide. For 2 centuries, it has been exploring systems that are either intrinsically simple or that are capable of being analyzed into simple components. The fact that such a dogma as vary the factors one at a time could be accepted for a century shows that scientists were largely concerned in investigating such systems as allowed this method, for this method is often fundamentally impossible in the complex systems. Not until Sir Ronald Fisher's work in the 20s, with experiments conducted on agricultural soils, did it become clearly recognized that there are complex systems that just do not allow the varying of only one factor at a time. They are so dynamic and interconnected that the alteration of one factor immediately acts as cause to evoke alterations in others, perhaps in a great many others. Until recently, science tended to evade the study of such systems, focusing its attention on those that were simple and, especially, reducible. In the study of some systems, however, the complexity could not be wholly evaded. The cerebral cortex of the free living organism, the anthill as a functioning society, and the human economic system were outstanding both in their practical importance and in their intractability by the older methods. So today we see psychoses untreated, societies declining, and economic systems faltering, the scientist being able to do little more than to appreciate the full complexity of the subject he is studying. But science today is also taking the first steps towards studying complexity as a subject in its own right." End quote. In the popular book The Fifth Discipline by Peter Senge, systems thinking was defined as the capstone for true organizational learning, and thus no graduate studies would be complete, nor could we conscience graduating any student without a thorough understanding of the importance and the application of systems thinking. Some say it is something we need now to hit everyone over the head with as often as possible until it is firmly embedded there. Another approach suggests that if we simply allowed students to observe the complexities of the world with natural curiosity and didn't straitjacket your thoughts with reductionism and inadequate frameworks and impoverished concepts and stultifying vocabulary, everyone would end up a systems thinker. This goes back to my point about using the word waste. If you didn't have a container in your mind for this prejudiced concept, if you didn't have essentially a garbage bin in your head, you would naturally start thinking of what else could be done with the outputs of any given system. There would be no away to throw things, no grave for the dead. In fact, the word and concept dead are also what I describe as evil ideas that inhibit systems thinking. Without these conceptual dead ends inhibiting thought and creativity, systems thinking, I allege, should just happen. The book Systems Thinking Made Simple, and despite its ability to tackle complex systems, it really is simple, claimed that systems thinking itself is the emergent property of any complex adaptive system. It says that systems thinking is a natural behavior that results from 4 simple rules of thought. Of course, when pieces of the puzzle are missing, it can be impossible to see the forest for the trees. If you're missing key rules of thought and key insights in your education, you might be so blinkered as to never figure out how to be a systems thinker. This is because emergent properties are, quote, features or qualities that only come into being or exist through the wholeness of a thing or system, and which therefore promptly cease to exist as soon as that system is dismantled. For example, for the purposes of analyzing its constituent parts, end quote. The usual example for this is the example of the watch, which is an oft-used metaphor used to help people understand this. Contributors to the website Quora.com wrote, quote, "The parts of the watch combined have more surface area and volume than the watch itself, i.e. collectively they take more space than the original watch, but they lack the watchness of the watch. The watchness here stands for time. The parts cannot show the time." End quote. We've heard mathematically the sum of the parts has to be equal to the whole, neither more nor less. Quantitatively, on the other hand, it is bigger, as in the watch example, but qualitatively it is greater. Take the flower, for example. It is beautiful in its wholeness. You may dissect it into parts, but you will never be able to reach its beauty. That would have got lost in the process of dissection itself. The flower in its wholeness is greater than all its parts combined. End quote. Now, these examples from average readers demonstrate that the public already has a pretty good understanding of the core philosophical tenets of systems thinking, whether they use the right vocabulary or not. In fact, I would maintain that both the reductionist tropes of science and the holistic tropes are natural ways that human brains perceive and parse reality, and have been part of our problem-solving toolkit all along. Both are emergent properties that come from formalizing our understanding of the world and how to adapt to it. The key is really knowing when to apply which lens and for how long. Systems thinking, which is holistic, you see, isn't really the antithesis of reductionist thinking, because the whole really is greater than the sum of its parts. And systems and processes that are reductionist or that are served by reductionism are part of the whole. Reductionism is nested within the holism that is systems thinking. It is a subset. Therefore, a systems thinker would know when to apply the reductionist model rather than throw it away. Basically, to paraphrase the wiki definition, quote, Systems thinking is about elucidating principles that can be discerned from and applied to all types of systems at all nesting levels in all fields of research. Every particular systematic way of viewing the world could be considered a subsystem, or reasonably be considered a specialization of general systems thinking, or as the goal output of systems science and systems engineering, where we emphasize generalities that are useful across a broad range of systems, as opposed to staying within the parameters of the particular models of individual fields of knowledge. End quote. So what is a system as defined by systems thinkers? Wikipedia tells us, quote, an early focus of systems theory was systems that maintain themselves in consistent or viable state through feedback. These self-regulating systems are found in nature, including the physiological systems of our bodies, in local and global ecosystems, and in climate, and also in human learning processes from the individual on to international organizations like the UN. System dynamics is an approach to understanding the nonlinear behavior of complex systems over time using stocks, flows, internal feedback loops, and time delays. End quote. Stocks, flows, internal feedback loops, time delays. In other words, systems theory is this neat way of looking at the universe that accommodates every possible interaction at every possible level, from the physical to the biochemical and on up to the sociobiological, the cultural, the economic, and the political. In such a worldview, everything is connected to and related to everything else. Key to this is a willingness to embrace things and behaviors that are non-linear, meaning, quite frankly, mostly unpredictable. Systems thinking isn't thinking outside the box. It's thinking both inside and outside the box. When you think outside the box, you lose all the wisdom and the benefits of everything you learned inside the box. So that doesn't make much sense. Systems thinking goes both inward and outward. It expands the box in all directions of space and time. And when you start expanding your consciousness that wide, well, you can quickly see why there would be no room for something like waste. Waste is such a bounded, small-minded way of looking at something. Are there any atoms at all of any material that have no further use in any other systems when you look at the sheer scope and scale of the ever-expanding universe? Only people traumatized into using exceedingly small parts of their brain could even think that way. And as they say, a mind is a terrible thing to waste.